Okay, let's dive right into this explainer and uncover an incredibly elegant engineering hack. It's a tool that quite literally prevents mathematical chaos when we're dealing with massive electrical grids. If you've ever looked at a sprawling power plant and wondered how engineers actually do the complex math to keep the lights on without their calculators just melting down, well, you are in the exact right place. So here's the core problem we're facing. It's the sheer nightmare of trying to compare actual voltages and currents across a mishmash of generators, transformers, and motors that all have completely different ratings. Imagine you've got a generator putting out 13.8 kilovolts, and that feeds directly into a transformer that steps it way up to a massive 132 kilovolts for long-distance transmission. Then, down the line, another transformer steps it back down to 11 kilovolts just to run a single motor. If you try to calculate the flow of power using actual volts, amps, and ohms across all of these wildly fluctuating voltage zones, the math becomes incredibly tangled. It's a massive headache. Section 1. Meet the per unit system, the universal translator. Now, the crucial point here is that instead of banging our heads against literal volts or amps directly, we express everything as a simple reference fraction. The per unit system takes all of those wild varying electrical quantities and just expresses them as a fraction of chosen base values. By doing this, calculating across wildly different voltages and equipment ratings becomes incredibly simple and, more importantly, entirely normalized. The contrast is honestly striking. On one side, juggling actual values is this messy reality where you're constantly converting between volts, amps, ohms, and watts. You're tracking decimal places, multiplying by 1,000 here, 1,000,000 there. But the moment we switch over to per unit values, everything becomes dimensionless and normalized. It entirely strips away those complex units, leaving us with just pure, clean, proportional math. Let's move to Section 2, establishing the base values, building the foundation. The entire system hinges on a very simple two-step process. First, you just pick a reference point, your base value. Second, you calculate your per unit value by taking your actual real-world value and dividing it by that reference base you just picked. And that's it. It is literally just a simple ratio. You'll need to establish these reference points across 4 core electrical quantities. We've got voltage, which gives us our V base in volts. We have current, giving us an I base in amps. We've got apparent power, or S base, measured in voltamps. And finally, impedance, the Z base, measured in ohms. Once you pick your base values for these 4 pillars, you are ready to translate the entire grid. Because you're dividing an actual value by a base value of the same unit, those messy units cancel out entirely. That leaves us with a pure, dimensionless number to work with. Keep this exact concept in mind. All per unit quantities, whether it's V per unit, I per unit, Z per unit, or S per unit, they are all dimensionless. Think about it. An ohm divided by an ohm is just a number. It's an incredibly liberating concept when you're staring down a mountain of grid calculations. Section 3. Important mathematical relations, the core equations. I'll slow down a bit for this one because this equation is absolutely critical. Notice how your base current is derived directly from your base apparent power, divided by the square root of 3 times your line-to-line base voltage. This formula perfectly locks your current base to the power and voltage bases you've already selected. And similarly, your base impedance relies entirely on squaring your base voltage and then dividing that by your base apparent power. The big takeaway here is how everything revolves around voltage and power. Once you define those 2 core values, current and impedance just fall right into place mathematically. All right, Section 4, tackling transformers. Let's be honest, this is kind of the boss level of power grid analysis. See, you can't just mash equipment together if their internal impedance percentages were calculated using entirely different base readings. Equipment manufacturers provide impedance values in percent or per unit based on that specific machine's unique ratings. It would be like trying to add US dollars to British pounds without bothering to check the exchange rate first. You need a common currency. So what's the fix? To analyze the whole grid as one unified entity, you've got to execute a change of base. You're basically translating every single piece of equipment onto a single common playing field. You have to convert all those individual manufacturer-provided per-unit impedances and voltages into one universal base before you can analyze the system. First up, converting those voltages. When crossing a transformer, you simply step your base voltages across it. You do this by multiplying the primary base by the transformer's rated secondary to primary ratio. This correctly links your voltage bases across the different zones of the power grid. Next, you update your impedance. Now, I know this formula looks a bit daunting at first glance, but it's really just proportional scaling. You are mathematically sliding your equipment's impedance over to your new unified grid standard. You scale the old per unit impedance by multiplying it by the squared ratio of your old and new base voltages and the ratio of your new and old base apparent power. Oh, and we all love a good engineering shortcut, right? Check this out. If your base voltage happens to stay exactly the same, meaning your old base voltage equals your new base voltage, that whole voltage chunk of the equation just turns into a 1 and disappears. In that case, you only need to scale your impedance by the ratio of the new base apparent power over the old base apparent power. It saves an absolute ton of time when you're working through a massive schematic. Bringing it home with Section 5, the key takeaways and our complete workflow. Let's pull this all together. Step 1, establish your common base by picking your overarching S base and V base. Step 2, translate everything from all those different machines into per unit values using those change of base formulas. Step 3, perform your complex grid math effortlessly using your new normalized fractions. And finally, step 4, simply convert your final answers back to actual volts and amps so you can operate the physical system. Ultimately, this entire system exists to give you absolute confidence when tackling the staggering complexity of a modern electrical grid. You simplify the calculations, you normalize the system, and you analyze with confidence. It truly transforms a mathematical nightmare into an elegant, highly scalable process. It really gets you thinking, doesn't it? If normalizing our variables works so perfectly for electricity, eliminating the chaos of wildly differing scales, what other massive, chaotic systems are out there, just waiting for the right common base to make them simple? Think about that the next time you're staring down a tangled, complicated problem. Until next time, keep looking for those brilliant foundational shortcuts.